Obviously a huge honor to get to give these lectures. And yes, I'm going to be talking about, well, novel states of matter. I'm going to try to tell you what that means. And in particular, despite the fact that I was raised a string theorist, my current research interest is mostly focused on something called quantum Hall physics. And the purpose of this lecture series is to hopefully, by the end of the day, have you guys understand what quantum Hall states are, why they're interesting, why they're maybe even useful. But from a more theoretical perspective as opposed to an experimental perspective, because I'm not good in labs. So let's start with what the basic question is. What happens if you take a metal, just a thin sheet of metal, and you put it in a strong magnetic field? What happens? And interesting things happen. If you just think in terms of classical electrodynamics, it's a metal, so there are a bunch of electrons moving around in it. If I apply an electric field in the x direction, and then you have kind of a magnetic field coming out of the plane, so this is a top-down view of your sheet of metal. Classically, what you expect is that the electrons will all just move in cyclotron orbits. And this is going to be pictorial. As we go through this later, I'll explain this in more detail. If I apply an electrical field to the right, if the magnetic field wasn't there, then what would you expect? You'd expect electrons are charged, so they'd start accelerating, and you'd get some charge current moving through the metal. But if you have a magnetic field out of the plane, what happens is that because of the fact that the electrons are trapped in these cyclotron orbits, there is no current in the direction of the applied electric field, but there is a current perpendicular. So this is something very funny, right? It doesn't conduct in the direction of the electric field, so it looks like an insulator. But it does conduct transversely, so it sort of looks like a conductor. This was originally discovered by Edwin Hall a long time ago, even before this lecture series was started. And in fact was discovered before people had come up with the understanding of electrons, that it was observed experimentally. This is not going to let me change slides. No, it's not. Right. So this is, as you can tell, I'm a physicist, not an artist. So this is my picture. I have my little slab. There's a magnetic field perpendicular to the slab, and there are a bunch of electrons in it. And so if I just ask if this is a regular metal, I can say the density of electrons, or the charge density, is going to be n, the number of electrons, times e, the charge of an electron. A minus sign because they're negatively charged. So let's look at this from a top-down view. I think of this, I just have some gas, it's top-down, so this is the magnetic field pointing out of the plane, and I saw these electrons here. And as I said, what happens? I apply an electrical field this way, and you see that the electrons move not in the direction of the electric field, but perpendicular to it. And it turns out, some people in the audience may in fact know this, this is actually just a simple consequence of special relativity, because I can go from the state with just a magnetic field to a state with a magnetic and electric field by doing a special relativistic boost. And if I boost down, that means the electrons are moving down. But it turns out, if you look at Maxwell's equations, that if I boost, you end up getting a cross product is what the electric field looks like. So B is coming out of the plane, V is going down, and so if you remember the right-hand rule, that means the electric field is pointing in the one direction left. And it turns out that just using these formulas, you can in fact calculate what the resistance is. Remember, Ohm's law is current is potential divided by resistivity, and here the current is just a stand-in for the total current running through. This is maybe a local measurement. And so you take these numbers, you run through them, and you find that this resistivity, which is something you can experimentally measure, is really simple. It's a function of the magnetic field strength. So the stronger the magnetic field is, the stronger this resistivity is. That means it's harder for them to move. And the more electrons, the easier it is to move, because if I increase the number of electrons, this decreases. So this is just it's a simple, straightforward theoretical argument. Now, what do you actually measure, right? You don't actually have this perfect piece of metal and you apply electric fields. What you actually have is you have this slab of thin metal and you put a bunch of leads at various points on it. So I have a left lead and a right lead, and I have some device that will drive a current through this system. And then I can measure voltage differentials, say between A and B or A and C, and the normal resistivity would be the applied current divided by the voltage difference between these two sites, and this odd or Hall resistivity would just be the applied current divided by the voltage difference across the material, right? And so people set out and measure it, and this is literally what you do in a lab. And it turns out that, so remember, I had this formula that said this should just be linearly increasing with B. If I have a piece of metal, I can't change the numbers of electrons in it very easily, but I can certainly dial the knob of the magnetic field, and that's what you actually do in a laboratory. And so what do you find? You find something very, very bizarre, as opposed to what I just told you. So this is a plot of the green curve is the normal resistance, and the red curve is this odd or Hall resistance. And you see that this red curve at very weak magnetic fields is fit very well by this linear assumption. But as you crank up the magnetic field very high, this magnetic field in Tesla, you see that something very strange happens. It stops being a nice straight line and it becomes these staggered plateaus. The standard nomenclature is that this big regime is called a Hall plateau. You see that it's somehow a perfect normal conductor because it doesn't resist at all, but the Hall conductance takes these very fixed values, and if you work through the numerology and you look at what these values are, this is 1, this is a half, this is a third, and you can see very quickly that it fits this very simple formula that for each of these plateaus, it just depends on a bunch of fundamental constants like Planck's constant, the electric charge, and n, where n is now just an integer. And it's 1 here, and it's 2 here, and it's 3 here, and so on and so forth. And this works amazingly well, and in fact, these plateaus are one of the best ways to experimentally determine the value of h bar over E squared. So something very funny happens here, and it gets even weirder. So here, remember, these are at least nicely labeled, 1, 2, 3, etc. But if you turn up the field higher, something even stranger happens. As you crank up the field way higher, so now we're going to 20, 30 Tesla, you don't just have these nice integer plateaus of 1 and 2 and 3 and 4. You end up getting plateaus not just when the value here that was an n, an integer, now it can just be what seems to be arbitrary rational numbers. So here, you go through the formula, you find that this Hall resistivity is for 1/3, here it's 2/5, 3/5, 5/7. Something funny is going on, and something that you might notice is that in all of these rational numbers, the denominator is always odd, which is maybe one hint that something funny is happening here. But it's not just arbitrary real numbers, it's particular rational numbers. It's very puzzling. And again, for each one of these places where there's a plateau, it's not always easy to see, but you recognize this plateau is also where the regular resistance drops down to 0. Is there a question?
The formula up there doesn't depend on magnetic field strength, the upper one?
No, it doesn't.
What is the driving of them?
That's the goal of these lectures, is to explain this. Yes, it's very, very strange, right? That I took a metal, and this is extremely robust. All you have to do is take a thin sheet of metal. You have to make it very, very cold, of course. But you do these experiments, and you see these plateaus are extremely sharply quantized. Now, some of them are easier to see than others. This 1/3 state that you may know if you've heard of Laughlin, Nobel laureate, he was the one who explained this state here. But all of these things are, to the best experimental accuracy, really do take these values for kind of a good chunk of that width. Yeah?
Is that pi?
Yes, so it's 2 pi h bar, so h bar is, of course, h over 2 pi.
Okay, I know totally nothing about this, but why would you have something that defines circles in this?
So that's actually just an unfortunate nomenclature. H bar is just a physical constant, and it's the usual version of Planck's constant, which is important in quantum mechanics. We'll get into that more next week. H bar is actually the original Planck's constant divided by 2 pi. So it really is actually just a fundamental constant divided by a fundamental constant multiplied by a rational number. You're right, it's maybe a little misleading that pi's are in there. But pi's show up all the time in quantum mechanics and in physics for reasons that maybe we'll get to.
And one quick one. Does that hold even for enormously strong magnetic fields?
So I don't know off the top of my head. Okay, so if you crank the magnetic field up way past this, and this is hard, it's hard to make magnetic fields really this strong. It's expected that other things will happen and this behavior will not persist forever, but it's just experimentally hard to do. There's something that I'm not going to talk about in detail called a Wigner crystal, which maybe should appear eventually at very high fields. But to the best of our ability experimentally, you see either kind of these boring intermediate regions or these plateaus that really always look like this. I think that there's at least experimental evidence of, since you'll notice that these numbers are decreasing as I move this way, there's a plateau that I know exists where this number is 1/5, and so that's even further out. So, right, so as we said, these plateaus are very strange, not just the fact that this particular resistivity is perfectly quantized, there are even more strange things that they do, and they really look different than normal insulators and metals. If I'm using words that are too jargony, please call me out and make me explain them. But everyone here knows what an insulator versus a metal, yes? Yeah.
Does this hold for any metal that's been tried?
I strongly doubt it, but it's a very general feature of something that looks, if you start with something where, before I put it in a magnetic field, and it looks like a standard metal in the sense of, we have theoretical models to describe normal metals. If without the magnetic field it really looks like a normal metal, and you make it has to be thin and two-dimensional, that's important, that it's not really thick. Because if it's thick, then you have to worry about movement of the electrons in that additional direction. But yeah, I think if you have a thin normal metal, this will generically happen in a strong field. But okay, so let me just mention, and I'm going to explain these in more detail what exactly I mean. So what are the interesting features of these things? So they despite the fact that I told you that it had zero resistivity, so that sounds like it's a perfect conductor, it turns out that there's a sense in which they are both insulators and conductors. I'm going to explain all of these points as we go through. And edge conducting means that it can only transport charge along the edge of the sample, not in the interior. And those charged excitations on the edge can only go in one direction. They can't go back and forth, only in one direction. And even weirder than that, if you have this funny state, it turns out that you can create particle-like excitations which have a fraction of an electron's charge, which sounds very confusing. And even weirder, those particles don't have to be bosons or fermions. They can be what are called anyons. And let's go through this. Right. So the first question, where are the mobile charges? What do I mean by that? Well, if something can conduct, then that means that there have to be objects within the material that are charged. And that's what we mean when we say mobile. It means they can move around. It turns out that when you try to probe these systems locally, so here again is my picture of this slab, I have the magnetic field pointing out of it, there are no mobile charges in the interior. If I try to locally drive a current between 2 points in the interior by kind of, attaching 2 leads and putting a battery in there and seeing if current will flow, it won't. Unless I turn on an extremely high voltage and really kind of break the system, essentially. But on the edge, you'll find that charge can move on the edge, but it can only move in one direction. So if I apply a voltage differential such that normal charge would want to move in this direction, then yes, indeed, a current will flow. But if I take that and I reverse it so that charges would want to flow in the other direction, you'll find that there's no current flow at all. So what that means is that these excitations at the edge are not like a normal electron, right? If I just had a piece of metal and I cut it, then obviously at the edge of that metal, there's no problem with charge flowing on the edge, just like the charge can flow through the bulk. Here's something very different is happening. It's really kind of one directional. And that's something that I hopefully will eventually get to explain to you. Perhaps even more interesting is this idea that these systems have excitations that are what are called anyonic. So let's explain what that means. So in normal quantum systems, if you exchange 2 particles that are identical, like a photon, a helium atom and a helium atom, does the state have to come back to itself? Now, classically, that seems obvious, right? If these two guys, I can't tell the difference between them, and I exchange them, why would I see a difference? But that's classical intuition, and it turns out that in quantum systems, that just doesn't have to be true. So I imagine I have two particles. I'm going to call one p and one p prime so I can keep track of them, but they're supposed to be the same type of particle, an electron or a neutrino or whatever you want. And in the lab point of view, I imagine I just take p and move it to where p prime was, and I take p prime and move it back to where p was. And in that sense, so psi is something called the wave function. How many people here have taken quantum mechanics? Okay, good. So at least you guys know what I mean when I say wave function. Next week, I'm going to go into this in significantly more detail. But you can think of this as basically a function that describes the state of the system. It has all of the information about what's going on in there. And here I'm saying it's a function of two positions, because I have two particles to keep track of, right? So there's a wave function of position x1 and x2. And so you can ask a very basic question. Well, if I move this from x1 to x2 and from x2 to x1, does the wave function have to come back to itself? And I just want to point out that if this is from a lab's point of view, if I imagine just looking at this from this particle's point of view, what I've done is I've taken this other particle and I've just dragged it around it, which is something that's called braiding. But for now, let's just think of this point of view, of just trying to exchange two particles. And the people who have taken quantum mechanics know this very, very bizarre fact that if you look at objects that are called fermions, and that's electrons, protons, neutrons, and so forth, it turns out that there's actually a minus sign here. The reasons for which are a part of a very beautiful story in quantum field theory. For now, we're just going to take this as fact. The definition of something being a fermion is that if I have two of them and I exchange them, this object, the wave function, that tells you all of the physics of where they are and kind of tells you the shape of where they are in terms of wave packets, has to pick up a minus sign. And that has an extremely important consequence. That tells me that if I try to put the two at the same position, so I just say x1 and x2 equals x1, well, by this formula above, that has to equal minus itself. So it has to be 0. And what that physically means is that you can't put two fermionic objects in the same place at the same time. This is something that you may have heard of called the Pauli exclusion principle. And it's just this simple algebraic argument is where it comes from, but it's extremely important. And the Pauli exclusion principle is, for reasons that I will not go into in too much detail here, the Pauli exclusion principle is the reason that metals behave like metals and not like something very different. On the other hand, if you have something that's bosonic, which sounds like an insult, but it isn't, it's just a name. Bosons, and bosons are just things like photons, or you've probably, of course, heard in the news about the Higgs boson. Bosonic particles end up getting a plus sign here. And that means that two bosons can be in the same place at the same time. I don't have something having to be equal to minus itself. There's no problem putting them in the same place at the same time. The fact that there's a plus sign so that you can put a whole bunch of, say, photons in the same state at the same time is the reason that you can have lasers functioning. What a laser does is it essentially makes a coherent set of photons piled up on top of each other, so you get one beam at one precise frequency. And the reason any of that works is because of the fact that photons are bosonic. And it's a fundamental kind of tenet of particle physics that fundamental particles, everything that's listed in the standard model, has to be one of these two types of particles. That's just one of the rules that's, is very, very strongly empirically dictated. But in quantum Hall physics, that doesn't have to be the case, right? Because we're not talking about fundamental particles. We're talking about having a very complicated system. All sorts of particles are interacting and moving around, and they're kind of emergent objects that don't have to follow those rules because they're not, fundamental particles in vacuum. And so this braiding procedure doesn't have to give me just plus or minus 1. So, right, if P was a fermion and I braided it around P prime, I have to come back to kind of minus myself in a way that I'll explain in more detail next week as I try to explain what these words means in a more specifically quantum mechanical language. But that minus sign basically tells you that if I want to come back to where I started, I don't just get to rotate by 2 pi to get back to where I started. I have to go around once more, and so I have to rotate twice around the circle. I have to rotate 4 pi to come back to where I started for fermions. And that doubling, that fact that you have to go around 4 pi instead of 2 pi, is actually, for fermions, fundamentally related to the fact that fermions have spin a half. And I'll just leave that as a tantalizing detail, and we'll explain. What?
What was that word?
They have spin 1/2.
Oh,
Right? Photons can have either spin 1 or spin -1 if you think of the 2 polarizations of a photon, but fermions have spin a half. Which we'll explain. So, for instance, you remember that I had that plot and there was this big wide plateau where it was 1/3. Well, it's known that for that 1/3 state, this is a very famous Laughlin 1/3 state, if I braid P around another one of itself, I don't get plus or minus 1. I get -1 to the 1/3, which is just a complex number. And so, if I wanted to get back to where I started, I don't have to braid once, I don't have to braid twice, I have to braid 3 times to get back to where I started, which is very strange, and is something that doesn't happen in regular particle physics. And sometimes things get even weirder, not for the 1/3 state, but for other conjunction states. You don't even get the same particle back. I could braid P around P prime and get not just, I'm not saying I get 2 particles after I braid. I'm saying that when I braid P around P prime, I get a quantum superposition of having gotten back Q particle and R particle. This is even weirder, and here we're already talking about kind of quantum superposition, and things are behaving very strange and very quantum. This is the nomenclature for this is non-abelian statistics, because the physics term for kind of this number you get as you braid things around each other is called the statistics of the particles. I don't know exactly what it has to do with Moneyball, but someone probably does. And this 1/3 for this particular particle comes along with the fact that this particle doesn't have a single unit of electric charge. It actually has 1/3 of the unit of electric charge, which is very confusing, right? If I ask you, okay, you have a bunch of electrons, they're in a metal, every electron has charge 1. How do you make an object with charge 1/3? It's a very difficult problem. That we'll hopefully explore. And that should be a hint that something really non-trivial and quantum and interesting is happening here. So that's my lightning overview of quantum Hall physics, which we'll be exploring in much more detail in the coming weeks. And I want to just point out now that these properties are fundamentally a consequence of having a whole bunch of electrons stuck together in a metal, and they're interacting very strongly. And by that, I don't mean the strong force of the standard model. I just mean that if you look at the actual strength of, charge-charge interactions between these electrons, it's not something small that you can ignore. And because of the fact that you had these funny statistical properties of braiding these particles, these are also possibly useful for trying to build a quantum computer. And this whole story, I think of as one of the most interesting examples of condensed matter physics. Now, I went back and I looked at kind of a lot of the titles of previous talks, and I saw a lot of things about particle physics and string theory and astronomy and things like that, and I felt like something crucial was missing, because condensed matter physics is an extremely interesting area of modern physics research. It's not obvious why someone from the EFI would be talking about it, but we'll get into that later. So what is condensed matter physics? And the name should kind of give it away. Is the study of systems with kind of a dense number of parts, a lot of particles all together at once. that you can think of the word condensed in condensed matter as thinking of, I have H2O condensed into water. So there are a whole bunch of water molecules all bouncing around off of each other. That's morally where the name comes from. You may also have heard the term solid state physics, which is a branch of condensed matter physics. And the goal of this branch of physics is essentially to describe the macroscopic properties of systems. By that I mean, measurements that you do at lab scale without zooming into the atomic level, right? Like I told you, right? You have a piece of metal, you attach some leads, you measure currents, you measure voltage differences. That's what I mean by macroscopic scale. And you want to see whether or not you can derive those properties from some microscopic understanding. If I say I have a metal is an ionic lattice, so there are a bunch of ions of atoms arranged in a lattice, and the outermost electrons are free to kind of hop around and go wherever they want. That's an example of how this works. There are lots and lots of interesting things in this field. You can talk about fluids, metals, superconductors, the list goes on essentially forever.
Can I ask a quick one?
Yeah, of course.
Is
Please.
superconducting then the reason we don't have a good model and explain it? Because it's really based in quantum mechanics?
Sorry, I'm not sure I understand.
It is to explain the theory of superconducting so we can predict what substances we need. And they can't seem to come up with a good theory of superconducting.
Well, so there is a classic theory of superconductance called BCS theory. It was invented by Bardeen, Cooper, and Schreifer, I want to say in the 70s, but I'm not a historian. And that works for most superconductors. I think what you're asking about are these kind of novel superconductors, often called high TC superconductors, where they behave in many ways like a normal superconductor, but some of the finer details of what the BCS theory would predict doesn't match. So that they still kind of have perfect conductance, they still repel magnetic fields, the usual kind of qualitative parts of a superconductor, but if you dig down into what the theory really is supposed to tell you in terms of what you measure precisely, not just phenomenological things, it doesn't quite work. So there are lots of people working on this, and they have various ideas. I think the fundamental underpinnings of why those things superconduct is known. It's just that there are essentially details missing, right? But we can talk about that at a later point. All right, sorry. Are there other questions? Great. So how is condensed matter physics different from, say, particle physics, something that I once studied, right? So this is the usual type of thing you see in particle physics. Does anyone know what this is actually a picture of? I'm curious.
Feynman diagram.
It is a Feynman diagram. What is it a Feynman diagram of?
Beta or beta?
Yep, it's beta decay. So what this is a picture of is this is a neutron. It's made up of 1 up and 2 down quarks. And one of the down quarks emits a W boson and turns into an up quark. And if you have 2 ups and a down, you have a proton. So this is if you just have a neutron, isolated, not part of a nucleus, not part of some nucleus. If you wait, I think something like 10 minutes or so, it'll decay. And this is the way by which it decays. And in that decay process, since the neutron is neutral, and a proton is positively charged, I have to emit something negatively charged. So you emit an electron, and you actually also emit a neutrino. And what I want to emphasize about this is that this is the usual picture you see in kind of standard particle physics talks. And the point is that there aren't that many particles, right? I started with 1 particle, I ended up with 3. That's not very many. I'm kind of working in near the vacuum, right? These guys can be interacting in complicated ways, but I don't have to keep track of too many of them at once. At least pictorially. An expert particle physicist could tear the details of that statement apart if they really wanted to. On the other hand, condensed matter, I'm supposed to have lots of particles bouncing around. So this is a picture of a very interesting material called graphene. It's a 2-dimensional sheet of carbon, and you find that the carbon atoms are just arranged in this beautiful hexagonal grid. And if I want to understand what's going on with graphene or any other metal or any other kind of solid chunk of matter, I need to be able to kind of keep track of all of the electrons going on in here. If I want to describe the system, I really need to be able to describe everything that's going on in here. So I have lots of particles bouncing off. I need to study the emergent phenomena. But it turns out that despite these pictures kind of looking different, you end up using the same basic tool. Kind of theoretical models in these pictures, the same basic tools are just quantum field theory, which is a souped-up version of quantum mechanics. And now, if you'll permit me, since I'm talking about the relationship between condensed matter and particle physics, and this is the introductory talk, so I'm not going to get into anything in too much detail. I'm going to get a little bit philosophical for a moment. And so, I'm a theoretical physicist. I'm not an experimentalist. I don't go into the lab and try to measure things precisely. I come up with theoretical models. So the question is, what is a theoretical model? And I think, unsurprisingly, Feynman put it best, and I can't do a Brooklyn accent, unfortunately. But what did he say? He said, in general, we look for a new law by the following process. First, you guess it. Now, let me put in a comment there. Guess sounds blasé, but of course you can make intuitive guesses or inspired guesses. So you guess it. Then you compute the consequence of the guess to see what would be implied if this law that we suggested is right. And then you compare the result of the computation to nature, via experiment or experience, compare it directly with observation to see if it works. If it disagrees, it's wrong. Right? And that's really how the game works. Right? So what is a theoretical model? A theoretical model is just a machine, right? It has inputs and outputs. The inputs of a theoretical model are kind of the state of the system and what you're going to do to it, right? So you say you have your material, it's 45 Kelvin, I apply some voltage, I apply some pressure, right? And the theoretical model is supposed to tell you what happens, right? So it tells you how the system responds, right? You say, maybe you heat it up, you measure some current response, it caught fire, lab burns down, something bad happens. This is the reason that I'm not an experimental physicist. Oh, okay, this is embarrassing. I left my note in about fixing this diagram even though I fixed it. Right. So, in a theoretical model, right, say I'm trying to describe a metal, okay? Do I really need to keep track of every single electron in that metal? Right? You have lots of complicated systems, you have many moving parts, they're all interacting. Keeping track of every moving piece is really just too difficult, right? If you wanted to try to keep track of every say, electron in a metal, even in some simplified way, there's no computer that exists that could do it. A mole is too big of a number. There are too many atoms in any physically reasonable piece of matter to keep track of all of them. Let alone, that's just keeping track of where they are. Let alone kind of trying to see what happens as you turn the system on, right? It's far, far too complicated. And so a key piece in trying to build theoretical models is asking the following question. As I'm describing the system, what information is really essential to describing the phenomenon that we observe? And what information can you ignore that you don't really need to keep track of in too detailed a way? So here, you kind of have the pictorial idea that a liquid is, of course, made up of a bunch of particles bouncing around, but when you think of a liquid, you don't think of those particles, you think about water flowing. Or similarly, right? If I have an atom, I know I can zoom in the middle of that atom, and I see that there's a neutron, or there's a nucleus, and it's made up of neutrons and protons, and each one of those is made up of quarks and gluons, and this kind of goes down and down. But if I'm interested in kind of some simple atomic physics, like what is the spectrum of a hydrogen atom, I don't really need to keep track of all these details, right? I can simplify my model and say that the nucleus of a hydrogen atom is essentially a single proton that's a point particle. I don't have to worry about the fact that it's made up of a whole bunch of smaller pieces. Right? That's what I mean by kind of when can you ignore things. And it turns out that over the past, let's say, 40-ish years in theoretical physics, thanks to work by, among many other people, Wilson, Kadanoff, Polchinski, and others, many, many others, that list is far too short. The key organizing principle in physics is organizing by scales, right? So in that picture of the atom, that's precisely what I meant. If I'm looking at an atom, if I'm looking at, say, the spectrum of a hydrogen atom, and I'm not zoomed in too closely, then I don't need to zoom all the way in. I can kind of look at the system at the scale of it just being one atom, so that's, you know, I don't know, 1/10 of a nanometer, not too big. I don't have to zoom way, way in. What do I mean by that? So if you look at behavior at large scales, you don't have to know everything about the microscopic details. Now, I should be careful about that, right? If you consider arbitrary measurements, arbitrary, finely detailed things, then of course you do need to keep track of everything, right? Because if you really zoom way in on some kind of, you know, higher, some larger atom spectrum, you zoom way in on each of those spectral lines, it may in fact be the case that you have to know the details of how the various components of the nucleus are interacting with the strong force, and you have to know much smaller details. But that's only if you zoom really far in. You look at really, really fine splitting. If I don't look too closely, I don't need to keep track of all of those details. Another way of saying this is, if you want to know how a truck rides, don't put it in the LHC, right? You're gonna, if you hit a system too hard with a hammer, you're gonna break it. And usually when we do lab measurements, right, we're not doing extremely violent things to our samples unless we're in a bad mood, right? When you apply an electric field to see the Hall effect, you don't apply an extremely strong field. It's a very weak one because you're kind of looking at kind of small responses. So let me give you an example of what I mean by that. Think of something really simple, a compression wave in a fluid, right? So what is a fluid? A fluid is a whole bunch of particles closely packed enough that they're bouncing together, and you see that it has some nice behavior. So if I have a fluid in a tube, and I kind of push one end of the tube, I know what happens. I could create a compression wave, right? What does a compression wave look like? Well, this is exactly the picture. Since I push the system here, the particles are more closely packed. And then you see that that compression wave will move. There'll be an increased pressure region, decreased pressure. And the shape, if I ask what is the pressure of the fluid as a function of this distance, you'll see that it'll have this nice wave-like behavior. And it turns out that in the study of fluids, I can essentially just keep track of what this profile of the pressure is and what the direction of the flow is. I don't need to know where every single air molecule or water molecule or whatever in this object is to know how a wave in water propagates, right? This is what I mean when I say you organize things by scales. Now, of course, if I push it really, really hard, I do have to know some of the details, right? If I really smash it so hard that something drastic happens. But, so the idea is that I can talk about this kind of, this compression wave being kind of long wavelength. And it turns out, if you think about a compression wave, there are basically two scales, right? There's the scale of how big the amplitude of this increased pressure is, and there's the distance scale of how long each piece of the wave is. And it turns out that the energy goes as, well, the square of the amplitude divided by the length of this wave. And it's very common in physics to not work with an explicit wavelength, which is a unit of length, but to work with an inverse wavelength, or to work with a wavelength k, which is literally just 1 over the wavelength. So I want to point out that how do I make these very low energy waves? Well, I can make the amplitude very small, or I can just make this wave be very, very long. And that's called kind of a long wavelength limit. And as the wave gets very long, that's the same as the wavelength of this k going to 0, right? And so this is, I want to point out this example to just emphasize that this is very, very common in physics. That is, if I look at the behavior of systems at long length scales, right? So I create a wave and it's very slowly varying. That's very low energy compared to the, rest energy of the fluid sitting on its own. So hopefully the point of that example was to make the idea that if you just are studying kind of long wavelength, low energy excitations, which is what you're looking at if I'm looking at, simple DC conductance of a material, right? If it's DC conductance, everything is kind of moving together. There's no fine-grained wave structure in it. Long wavelength, low energy excitations, by that argument, don't always need to keep track of everything. They'll know some key properties of what you started with. You know, if I started with a metal, I need to remember that it's metal, so there are charged things moving through it, but I don't need to keep track of where every single electron is. So this is basically the idea. This principle, the physics nomenclature is renormalization group flow, but you can just think of it as coarse graining or squinting, right? If I zoom really close in, I have a whole bunch of water molecules bouncing around, but I don't need to keep track of every water molecule to see that water flows. Is that clear? Right. So, yeah. Right, so because of the fact that I can make this relationship between the length scales in my system being large and the energies being smaller, energy scales usually are more commonly used than length scales to organize your system. So you don't need to know string theory to describe classical general relativity, even though we've all been told that string theory is, the grand unified theory of quantum gravity, but you don't need to know it. You just need to know GR. If you're looking at things at kind of astronomical scales, you don't have to care about the fact that, well, what is quantum gravity, unless you're worried about black holes evaporating or something like that. So you don't need to know all of the details of QCD to describe basic pion physics. You don't need to know all the details of the standard model to describe QED. Of course it helps, right? If you have an idea of what the microscopic description is, it can give you some intuition as to what to expect at long distances, right? Because it's not always possible to say, so for instance, QCD is a good example, right? QCD is the description of the strong force between quarks. And the reason we call it the strong force is because it's very, very strongly interacting. And so if you try to just sit down and do a calculation of what happens if I just take a bunch of quarks and they have very strong interactions with each other, what do I get as an output? We don't have a mathematical framework to do that calculation other than basically putting it on a computer and trying to intuit what the numerical output is, right? But you kind of you can look at QCD and say, well, if I look at the charges of each of the different quarks and I put them together in different combinations, I can get something that has the same charge as a proton, the same charge as a neutron. But there's no explicit mathematical calculation going from starting with strongly interacting systems and going to QED with protons and neutrons. That's what I mean by it helping. So having talked about condensed matter for a long time, I feel like I should give it the EFI sales pitch. The EFI is usually thought of as a place where people study high energy physics, right? There's the James Franck Institute. That's where condensed matter is supposed to go. But as I've tried to argue, the fundamental tools in theoretical physics are really, there's no sharp divide between the tools you use for high energy physics and condensed matter physics, or solid state physics, right? You're still basically using this thing that I've mentioned a number of times called quantum field theory, which is just souped up quantum mechanics, right? There are often linguistic divides, right? The people will use different terms depending on what culture they were raised in to describe what is essentially the same thing, but a lot of the phenomena are really the same, and many really important discoveries on both sides have helped connect the two. For instance, since it was mentioned earlier, superconducting metals, the fundamental reason that metals, when you cool them down to a very low temperature, that they superconduct, shares much of the same physics as the Higgs mechanism, which we've all heard is the reason that particles have mass. Now those sound like two completely different problems, right? One is some fundamental question about why things have mass, and the other is just you take a metal, you make it cold, and then magnets float on top of it, right? But there's a sense in which the underlying physics explaining what is happening in both cases is really the same. And looking at problems from both sides, from new perspectives, can often give you new insight and new ways of thinking about these things. This sales pitch is strongly tied to the fact that, as was mentioned, I'm a member of this institute called the Kadnoff Center. And what the Kadnoff Center is precisely this. The point of the Kadnoff Center is to try to bridge these two communities, the high-energy community at the Fermi Institute and the condensed matter community at the Frank Institute. And because of the fact that, especially in recent years, there's this very strong overlap in both fields, and there are people working with each other. As I mentioned, right, I got my degree in Santa Barbara as a string theorist, and now I'm talking about condensed matter physics. And I'm certainly not the only person that has done that, and people have gone in both directions. So usually it's people fleeing string theory to condensed matter, if we're going to be honest about things. But, you know, because I learn things in a slightly different language, it gives you a new perspective and can often help you think about things in a new way, which always helps. So, solid-state systems can give you lots of different materials, different samples that you know kind of, it's not the same types of atoms making up, that exhibit kind of very similar behavior. And so, the focus of condensed matter physics is understanding why these things look similar. This is something that's sometimes called universality, though that maybe is a more technical term. Right? For instance, I can take lots of different types of metals, and if I cool them down, they'll still superconduct. Right? So there's some sense in which the behavior of superconductivity is kind of universal. It's something that kind of has to happen if you take a metal and you make it very cold. And having all of these different materials to play with experimentally gives you the ability to explore what's often called theory space, right? When I cook up a model, there are lots and lots of different models I cook up. And it's only by doing experiments that I can know whether or not a model was actually worthwhile to describe the real world, right? And so, from a theoretical perspective, of course, something that's very interesting is to try to come up with models that explain experiments. But there's another part of it that I think a lot of theorists really like, which is this idea of exploring the theory space and trying to understand kind of what theoretical models can occur in real life. Are there any that are hard to find? You know, why do some theoretical models just look nothing like real life? Well, we should just ignore them. Are there any theoretical models that are forbidden in the sense that there will never be a laboratory system that realizes them? You know, these kind of broader questions of kind of what the kind of the realm of different theoretical models looks like. Exploring that is kind of the theorist's analog to going in a lab and trying to do a bunch of different experiments. Except we don't have to get our hands dirty, except for when your pen breaks.
Could you even talk about forbidden model?
Sure. So an example of a forbidden model would be the following. In quantum mechanics is a statistically predictive system in the sense that, you know, as people who have taken quantum mechanics learn, and we'll talk about more next week, when you do calculations in quantum mechanics, your answers are statistical in the sense that you have to go into the lab, repeat the experiment hundreds or thousands of times, and then kind of plot a distribution of what you saw. And quantum mechanics tells you what those distributions look like. Okay? And so you could cook up models, so for instance, so there's kind of a notion of probability distributions are part of what quantum mechanics are describing. And so you can imagine if I take the system and I evolve it forward in time, probabilities may change, right? If I take my system and I do something to it, then now after, say, having applied a magnetic field, I find that my electrons are now statistically more likely to be spin up than spin down, okay? But we're talking about probabilities, and so if you're talking about probabilities, when you add them all up together, you better add up to 1, or you're not doing statistics. And there are models that are called non-unitary models, where when you go through the rigmarole of doing these calculations, you find that when you do certain things to the system, the probabilities don't add up to 1. That's a sense of something that I would just consider forbidden. It kind of doesn't make sense. And certainly when you do experiments, that's not how you interpret things. Another one, maybe a little more mundane, would be a system describing charged particles that doesn't have charge conservation, right? We all like charge conservation. It makes a lot of sense. the reason we like it is that it's so robustly experimentally verified, right? So you can always write down a model where charge is no longer conserved. I can just have a proton, and it can turn into a neutron without having to eat an electron, right? But there's both physically a sense in which you never see that, so it doesn't make sense, but there are also kind of mathematical reasons that those are kind of unsettling. And so when I say forbidden, I mean kind of that from both ends. Forbidden maybe from a experimental perspective, it's just something that you don't think you'll ever observe, and also something that maybe either is mathematically internally inconsistent, or, and this is probably more kind of to one's taste than really being forbidden, it's something that seems icky, for lack of a better word, right? There are theoretical models that just seem too convoluted to really be like real life. Now, you have to be careful when you say things like that, right? If you think about the standard model, the standard model has this whole host of particles, and it has, particles on all sorts of different energy scales, and you say, well, that seems like a really convoluted mess, right? So part of theoretical particle physics is focused on trying to come up with a model that explains in kind of a nice way why the standard model looks like it is. Those are called grain unified theories, that type of thing. So this notion of exploring theory space is certainly not unique to condensed matter physics. It's kind of a lot of theoretical physics. So as we wrap up, I have to point out that as a theorist, the language of theoretical physics is math, and not everyone, fortunately, is a mathematician. Okay. But it's difficult to talk about a lot of the aspects of theoretical physics, especially the things, recent interesting developments, without at least making some appeals to mathematics. For instance, earlier I talked about wave functions, and so to know what a wave function is, you have to know what a function is, so on and so forth. I'm going to try to make things as kind of pictorial as possible, to try to explain things, and if I go through something and the math is a little rough, call me out on it. I'm happy to explain things in more detail. But I do want to take a poll of the room. How many people here know linear algebra? And when I say linear algebra, I mean, matrix multiplication. Who here remembers matrix multiplication? Fantastic. That is a lot more than I was expecting, and I will have a lightning review of it next week. If I have time, I will try to even put something up on the website. I was asked earlier, let me just comment on this now. I was asked earlier about having the slides available on a website. So there is a website on the EFI website for the Compton lecture series. If you just go on Google and type in EFI Compton lectures, you will find that. Now, at the moment, it is currently just a listing of the schedule and my abstract and so on and so forth. But this coming week, we will make sure that my slides will be up there, as well as I will try to put up some suggested, light Wikipedia readings for people who need a small math refresher. But yeah, so I don't know it off the top of my head, but Google EFI Compton lectures, you'll find the website, and slides and other things will be up there. So who here? So linear algebra. I'm happy so many people remember it. Who here remembers calculus, and I really mean kind of one-dimensional calculus, really just kind of functions. This is great. Good. All right. That means I can actually talk about Hamiltonians. All right, so, yeah, all right, so with that, I think it's time to start wrapping up. So I'm just going to kind of roughly talk through the outline of what I aim to talk about for the rest of this quarter. So we already talked about this. We already talked about today. So next week is going to be about the fundamental principles of quantum mechanics. So sorry, I asked this before, but I want to remind myself. How many people here remember kind of quantum mechanics at the level of they know what the Schrodinger equation is, they know how to take expectation values of operators? Good, okay. If you know linear algebra, you secretly know how to do all of those things. Don't worry, it's the same thing. It's just the physics words instead of the math words. So next week is going to be talking about kind of really the principles of quantum mechanics, why it's so different than classical mechanics. I'll talk about the notion of entanglement. First, because entanglement is really cool, and second, because it's actually also a very active research of physics right now, despite it being something that every physics major learns their second year. The week after that, I'm going to talk about something called electronic band theory, which is a way of understanding metals before you put them in a magnetic field. And this is really something that's called a many-body warm-up. So I mentioned before quantum mechanics versus quantum field theory. Those are words. The only difference, both of them are quantum systems. Quantum mechanics usually refers to the study of kind of one or maybe a few particles at a time. For instance, if you have a very heavy hydrogen atom and you have an electron orbiting around it, you can kind of ignore the details of the hydrogen atom and study the behavior of that one electron. That's a quantum mechanics problem. Quantum field theory is when you have lots of particles and you have to keep track of all of them at once. That's really the only difference. So the week after that is the Leo Kadanoff Memorial Symposium, so there won't be one of these talks, unfortunately, but there is the Memorial Symposium. The week after that, I'm going to be talking about, these are words, really this lecture is going to be describing a lot of stuff that Leo worked on and was famous for, having to do with critical phenomena, renormalization, and things like that. The week after that, I'm going to start finally digging into the details of what happens when you take a metal and put it in a strong magnetic field. These things that I kind of teased in the first half of this talk. And then we'll continue that by really talking about the fractional quantum Hall effect. Fractional is just the name for when you had those plateaus where the number was a fraction and not an integer. Motivated by looking at these systems, the week after that I'm going to talk about quantum computers. You don't need to know how to build a regular computer to understand this. I'm just going to explain kind of what the difference is, why the idea of being able to have a quantum computer is so useful, and since the tools in a lot of these systems can be used in theory, people haven't really done it yet, to build a quantum computer. That's one of the strong motivations for looking at these things. And then the final week, I'm going to try to give kind of a broad overview of not just quantum Hall physics, because that's one of my specialties, but I'm going to talk about kind of on a more broad scale, what is the broader view of kind of the cutting edge of solid state theoretical physics, what people are working on. So with that outline, and if you'd like a copy of this, the handout this week is just a copy of this schedule. Thank you. Question?
You mentioned the language of physics and the language of mathematics.
Yeah.
And I'm just wondering, since you're a grandson of Feynman's starting point of intuition of why he chose that one over against Taylor's mathematical version of study.
I mean, you can, if you want it to be linguistic, Feynman diagrams are really just a subset of graph theory, which is a piece of math. I mean, you're drawing diagrams, and there is a mathematical study of the different types of structures that you can have in diagrams. They're of course equivalent, but for my money, it's much easier to just draw a bunch of diagrams, say what each piece is, and write down the answer, than do every single Wick contraction until you have the answer. Does that answer your question? Yeah.
I guess maybe if you're going to get to this is something I'd like to be entanglement, I think. So you got two particles, they're separated each end of the surface.
Yep.
You do something with this, it automatically knows which is this. But that violates the thing that information cannot travel at a speed faster than the speed of light. Am I right there?
So this is kind of a two-part answer. So you're absolutely right. So the idea is the following. Entanglement means that I can have two electrons, so I haven't talked about the detail, but electrons have spin, and for our purposes, let's say that spin can be either spin up or spin down in the sense that it's spinning on its axis. Is the axis pointing up or down? Okay? And because of entanglement, I can imagine I have one spin and it's up or down, or a superposition of up and down. And if I have two electrons, I can say they're both up or they're both down, or I'm in a linear superposition of both up or both down. All right? And in that case, they're entangled. So what does that mean? If they're both up or both down, and then I take one of the electrons and I separate it, and I ask it, I do a measurement. I say, are you up or down? Right? Now, this is a statistical question, and it turns out that it's both up or both down. There's a 50-50 chance. that it's up or down. So say I have my guy all the way over here, I measure it, and it's spin up. Now I know that he over there, if he then consequently does his measurement, he has to get spin up. Okay? Now, your concern is about propagation of information. There's no way to use that entanglement to send information. Okay? You know it, but you can't tell him that. Other than sending a light signal. He would do the measurement on his own, but he would know that you had already measured yours until you told him. So he'd have to send a signal. So it is true, it's weird and conceptually funny, but you can't use entanglement to send information faster than the speed of light.
That was the key.
Yeah.
Okay, interesting.
Yeah.
Yeah, well, the underlying phenomenon that permits this effect, that two particles are connected at great distance, that's not understood, right?
I mean, it's
observed, but not explained.
there's a mathematical framework that describes it and agrees with experiments. Now, that's a mathematical framework. I'm a physicist, not a philosopher. So I need a machine that gives me answers. Now, if I sit down and think about what it really means for me to do a measurement here and then know that something else happens over there, you can take, okay, conceptually that's weird, but it works. That's just the way the world is. Now, you might, there are rabbit holes you can fall down of in terms of kind of many universe theories trying to interpret what these things mean, but quantum mechanics is just you don't have to fall down that rabbit hole, and it can be dangerous, because I've spent enough time thinking about it and never really felt like it was worth my time. As a physicist, I wanted to be able to explain the things that I see via some toolbox. I don't need to, what does it mean to, conceptually understand, why things are the way they are? They're the way they are because you do measurements and it agrees. That's physics. It's not always a satisfying answer, but again, I'm not a philosopher.
Yeah, is there any solid-state analog of the non-locality of string theory? Instead of the kinetic energy being p squared, it's like e to the minus p squared in string theory?
You don't actually even need to do that. There are solid-state systems. Right, so string theory, as it sounds, you guys, I'm sure, many of you have heard versions of these lectures about string theory, and the whole point of string theory is that you don't have point particles, you have extended objects, right? So if you just mean that notion of non-locality, then there are condensed matter systems where the excitations are string-like, not point-like. And you can watch them propagate in their stringy ways, you can kind of get them tied in knots and all sorts of things like that. I mean, you don't even have to get into convoluted things like that. If you just want to see the behavior of extended objects, an amazing professor here at Chicago, William Irvine, does these fantastic experiments. He must have some of them on his website, where he just takes boxes of water and is able to excite in them vortex tubes. A vortex tube is already an extended object, and he can get them tied up in knots and watch how the knot evolves in time. So extended non-local objects are not hard to build in condensed matter systems. If that's what you meant by non-locality. Yeah.
So, going back to your earliest diagrams, both the handwritten one and the more formal ones, I'm starting off looking at that. Right off the bat. I started off in a state of, I can feel my brain quivering in useless emotion, because I have this problem. Having listened to lectures here going back even long before Professor Wakely, and having read a whole lot, I look at that and say, I'm confused about whether I'm in the classical physics realm or the quantum mechanical realm. Really, I feel like I'm in both and at once, and that's why the brain is quivering. So what I mean is this. You're talking about positions of things, and that's a very classical concept.
It is.
I have heard so many people in quantum mechanics lectures, and even read people like Schrodinger and Bohr himself talking about the meaning of quantum mechanics. Everything is a probability. It's all you can predict. And the people who take that, or make statements in that regard in the, let's say, the purest, most conceptual sense, will say things like, in quantum mechanics, the electron has no position until you measure it to find a position.
Yes.
And so, up until then, you can say nothing. Quantum mechanics says nothing about it except what the probability distribution will be when you do it over and over and over again. So how can you meld the two?
Sure. So at least on this slide, I have the word classical there. So that's my first defense.
Okay.
So yeah, no, this is supposed to be really the naive picture, right? So of course, when you go and look at the actual quantum structure, it isn't really like this. This is just supposed to be the classical picture. And it's not even a good classical picture because I have all of 6 electrons and I'm supposed to have a mole of them, but I can't draw that many E-minuses on the plot. No, I mean, you're absolutely right. This picture here, and more importantly, this picture here, where I make this caveat to special relativity, is a explicitly classical statement. Okay? And this result, the fact that this resistance goes as B divided by charges, is a classical result. And that's why I can talk about electrons being in places. And then, when you go to this picture, right, I don't actually know where anything is. What I really know is where the leads are in the measurements that I do. Now, it's of course very helpful to kind of think to yourself that, okay, if I don't know exactly where all of the electrons are, but you know, morally speaking, how many of them are there, right? And you can ask, maybe this E isn't just localized here, but it has some probability distribution, that type of thing. And as we'll get into next week, yes, this question of kind of what does it mean for a particle to not be sitting at a point, but to be described by this thing called a wave function, that it's, I want to be careful because a wave function is not just a probability distribution. If it was just a probability distribution, then all you would be doing is taking classical physics and statistically averaging over different configurations. A wave function has more information than just probability distributions. A thing that you can do with a wave function is, among other things, ask, if I just ask where it is, what are the statistical probabilities of where I'll find it? But there's significantly more information in it, which kind of, to use language, that's where the quantumness is in the fact that it is a wave function and not a probability distribution. But we'll get into that in more detail next week.
Are you hinting at the fact that an electron is not a point particle, but like a packet of waves or a wave spectrum or something? It's not in one point.
I mean, it's related to that. But again, yes, the idea is that when you describe it as a wave has more information in it than just an amplitude. Because, I'm not explaining, I haven't explained it here, but so for instance, if I'm just looking at one electron, the wave function is a function of, at every position, there's a complex number. And a complex number has an amplitude and a phase. The amplitude tells you the probability. The question is, what is the phase telling you? The phase is basically a lot more information that if you just ask where it is, you don't know. But if you ask other questions, you can learn more, hopefully. Another question?
What be an example of some information that is provided besides, just the probability distribution of the wave function? What makes a wave function distinct from just a probability distribution?
So the more information is in there is in things like asking about more than just where that particle is, but I've asked, where that particle is, if I had done something to it, or if I had put another electron somewhere else, right? If I'm just thinking about classical physics, it's natural to just say, if I ask where the particle is, then I can keep track of the particle and I'm done. The wave function is more about that. It tells you about kind of how the system will evolve if you do various things to it, if I apply an electric field or magnetic field, so on and so forth. But I'm not sure how good of an answer that is. It should be hopefully more clear next week as I go through it in examples. But one way of thinking about it is this example of, and so it's not wave functions exactly because it's not functions of position anymore, but this question of, I have, entanglement between two electrons spin up, mixed with two electrons spin down, right? I can't describe that with just a probability distribution for each particle independently. I need a wave function. In that case, it's kind of a boring wave function because the position is now just up or down. But that's an example where you can very explicitly see that it's more than just a probability distribution for each particle. It also tells you about correlations between different particles. Is there another question? Yeah.
I'm a lay person who's never taken physics or mathematics. But I also assume that entanglement came from a theoretical point of view originally. And I also suspect that it's somewhat related to these so-called quantum Hall effects.
Entanglement was, of course, first when people were developing quantum mechanics. They saw this thing and they didn't like it, of course. It was very confusing. It was first, I'm not sure if discovered is the right way, but it was first realized that quantum systems could be entangled from a theoretical perspective. But it's not just a theoretical notion. It's something that you can experimentally verify, that you can create entangled states, and there are observable consequences of the entanglement. So it's, while it was originally thought of as a consequence of this mathematical framework, it's a real physical thing that exists and is observed, not in the sense that you can see that it's linear superposition of ups and downs, but that having linear superpositions of ups and downs has explicit, observable consequences that you could not see if you only had kind of classical probability distributions and not full quantum mechanics.
I guess really the question will come to this. Currently, Harvard, which is in Canada, and some university in China, has now reduced that distance of interactions, the distance for entanglement, to, I forget what the distance is now.
6 kilometers.
What?
6 kilometers.
Yeah, 6 kilometers. Why are we at that point and not beyond? What is the limiting?
Oh, okay, sure, good. So of course, if I just talk about this perfect world where all I have is 2 electrons and I just want to put them into a particular state, that's a very nice, simple mathematical story. But of course, in the real world, you have to do things in a lab, and labs are never perfect. So there's this notion called decoherence, which basically is the fact that if I had these electrons and there were 2 spin-ups and spin-downs, but they were really in a lab, say I had them in some vacuum chamber, but it's an imperfect vacuum chamber, then I try to cut down the interactions between those electrons and the rest of the world as much as I can, but I can never do it perfect. In a perfect world, you of course do it forever. But just real-world laboratory limitations are the reason that, you can only hold these objects in superposition for so long, and so if you want to separate them, you have to do it that way. So, but that's a, that's kind of a laboratory imperfections problem, not a fundamental problem.
So would that make you pessimistic about applying it to quantum computation? Would that be the case?
No, because for quantum computers, you're doing calculations fast enough that if you get a bunch of superconducting qubits put together, you could I think probably state of the art is at the moment it's not perfect. It's probably of the order of 5 to 10 qubits working and maybe doing some simple algorithm. But again, those are all at some point those become engineering problems. Now we can try to come up with things that are kind of more robust qubits, and that's a good avenue to take from a theoretical point of view. But I don't think there's any fundamental physical limitation on building a quantum computer. I think you just have to hire really good engineers to build it.
Just one quick one, I won't ask you anymore. But you brought up superconducting, it produces current along the edge. So
You mean the Hall effect?
Pardon?
The Hall effect has this edge current. What I was
Oh,
saying.
the Hall effect,
Yeah.
well, not superconducting. Oh, okay, yeah, the Hall effect. Okay, cool.
Yeah.
Are you going to hand out weekly summaries before the lectures?
They may be more, so the slides will be online, and my plan was to have the weekly summaries be more of a kind of, some not a detail of everything I talk about, but kind of pointing out the important things and maybe things that I don't have enough detail to go into here. And brief refreshers of maybe some pieces of math that are useful.
Well, I was thinking that would be a good place to put down the email address for the lectures.
Sure, yeah.
Okay.
Thank you.
Any other questions?